Here we have a car that starts from rest with acceleration of 10 meters per second squared for 10 seconds. It then immediately decelerates at a rate of 4 meters per second squared for another 25 seconds before coming to a stop. We are interested in finding equations for acceleration, velocity, and position in terms of time for the entire motion. We also wish to graph these as a function of time. So let's look at two phases of motion. Phase 1 acceleration is 10 meters per second squared. So if I graph this, and let's say this is A versus t, acceleration as a function of time in terms of time. For the first 10 seconds, let's say this is 10 seconds, and let's say this is another 25, therefore I label this as 35. Acceleration is constant for the first 10 seconds, so I draw this representing acceleration for the first 10 seconds, and then it decelerates. That means a negative acceleration, so I draw this as as a negative 4. So let's say this is the acceleration diagram as a function of time. Let's consider the fundamental equations of kinematics for rectilinear motion. If I let x represent position, then definition of velocity is derivative of position with respect to time, and acceleration is dv dt, derivative of velocity with respect to time. Since acceleration is given, I use the third relationship to solve for v. Therefore dv equals to a dt. If I integrate both sides of this equation, I can write v as at plus some constant. For the first 10 seconds, acceleration is 10. Therefore, for the first part of motion, velocity equation is 10t plus a constant, but since it begins from rest, that constant of integration is 0. So this is the equation of motion for velocity for the first part. For the second part, we have acceleration as minus 4, which is a d. V for the first part is 10t, and for the second part is, we found, minus 4t plus 140. Then if I integrate velocity 10t dt for the first part, I get 5t squared plus some constant of integration, and since it begins from rest at 0, we assume that initially it is located at origin. Therefore, this constant of integration is 0. And after 10 seconds, x of 10 is 5 times 10 squared, which is 500 meters. It has traveled to get the equation for the second part of motion, x equals to integral of minus 4t plus 140 dt. Integrating this, we get minus 4 halves t squared plus 140t plus some constant of integration, which can be evaluated as follows. If I plug, let's see, 10 seconds in this equation, I get the following. 500 equal to minus 210 squared plus 140 times 10 plus c. Solving this equation for c, we get, let's see, 700 minus 1400, we get minus 700. Therefore, the equation for position for the second part as a function of time is going to be minus 2t squared plus 140 t minus 700. So this is the equation for the second part, and here we have the equation for the first part. X equal to 5t squared. I wrote the second equation first and the first equation next. So now let's go ahead and graph the x equations. Observe that both of these equations are quadratic in nature. They are second degree equations. The first one has a positive leading coefficient, meaning parabola is going to be concave up, and the second one has a leading coefficient of minus 2, which means that parabola has to be concave down. So let's go to the next page and graph these. What I'm going to do is I want to also redo the velocity and acceleration diagrams and see the correspondence between them. So let's say this is A versus T. Let's say this is V versus T, and let's say this is X versus T. So we got A on this axis, T, V, T, and lastly X as a function of time. Recall that acceleration was positive for the first part and negative for the second part, so this is how I'm going to graph it. And velocity is integral of constant, which is a linear function. So let's draw this for velocity, and position is a quadratic function. Therefore, let's see, it is going to be a parabola concave up to the first 10 seconds, and for the second part it had a negative leading coefficient, therefore it is going to be concave down. If I apply the time values of 10 and 35 in the position functions, I can find the values for x at the corresponding times. At 5 seconds it is 500 meters, and if I plug 35 in the second position equation, I will get 1750 meters. This is 10, that is 35, 10, 35. Observe that if you look at the last diagram, the x diagram, derivative of x is v. Since this is a quadratic function, x is a quadratic function, its derivative has to be a linear function as depicted in VT diagram. And since acceleration is derivative of velocity, observe that since the VT diagram has a constant slope, acceleration is going to be a constant numerical value. Thanks for watching. See you in the next video.